Dr. Tasdizen is a professor of electronic and computer engineering and a faculty member of the Scientific Computing and Imaging Institute at University of Utah. He is particularly interested in deep learning applications where labeled data is scarce, and researchers alternative methods of supervision and semi-supervised learning approaches for solving these problems. He has served as an associate professor for IEEE transactions on image processing, IEEE signal processing letters, and BMC bioinformatics, area chair for MICAI, and currently serve as a senior area editor for IEEE transactions on imaging processing. His speech title is STEM-based transactive learning for histopathological image classification. Prof. Tasdizen, please share your screen.
Okay, can you see my screen?
Yes.
And you can hear me fine?
Yes.
Okay, thank you for that kind introduction and the invitation to speak today at MyCAD. So my interests in research lie in using datasets with limited labels, especially in the medical domain, and approaching this problem from the semi-supervised and self-supervised learning angles. Before I talk about that, though, I want to motivate today's talk by talking about histologic growth patterns in kidney cancer. Kidney cancer is one of the most prominent cancers worldwide, with approximately 79,000 new cases diagnosed annually in the US alone. Also a leading contributor to death, about 14,000 deaths annually in the US. 1/3 of newly diagnosed cases already will have metastatic cancer. Another third will metastasize in their lifetime, and the 5-year survival rate for this particular cancer is approximately 71%. And predicting the risk of metastatic progression after surgery is an important problem, but remains difficult. And one of the difficulties with kidney cancer is that it displays heterogeneous tissue morphologies. So these tissue morphologies, named as histologic growth patterns, or HGPs for short, include structures, architectures such as small nests, expensile nests, fused nests, rhabdoid, sarcomatoid structures, etc. So my collaborators in pathology studied the prognostic value of a large number of histologic growth patterns for survival outcome. And they grouped these growth patterns into 3 classes based on looking at the hazard ratio of metastasis. So favorable growth patterns have significantly lower hazard ratios, and non-favorable ones have significantly higher hazard ratios, and indeterminate ones are the ones that fall in between, that don't seem to have any significant difference from normals or from controls in terms of hazard ratio. They also studied the distribution for the number of distinct HGP types in a case, and this graph on the right shows that on average you can find 4 to 6 types of HGPs in a case. And looking at the distribution of metastatic versus non-metastatic cancer, one can see that risk of metastasis increases with the number of distinct types of histologic growth patterns found in a case. So based on these findings, they defined low and high risk groups. The low risk case they defined as no non-favorable histologic growth pattern and up to 2 indeterminate HGPs in a case. And the high risk group is defined by the presence of a non-favorable HGP or more than 2 indeterminate ones. And then they were able to show significant differences in overall survival probability between these 2 groups. The question we are looking at in my group is, can we automate the detection of HGPs in whole slide images to turn this into a useful tool? So as we know, whole slide images are very large images on the order of hundreds of thousands of pixels across. And the way we work with these images when using deep learning methods such as a convolutional neural network is to typically crop them into smaller tiles, such as 512 by 512 pixels, and feed them individually to a convolutional neural network. Then that brings the question of how do we train such networks? And a typical way is to use weak supervision. Weak supervision is popular because case level labels for these images are easily obtained from reports by using some language tools to extract keywords from reports, for instance. And then we can use multiple instance learning. Tiles from the same slide form a bag, and we can get the labels for each bag based on the case level reports. However, this approach, of course, necessitates a large number of whole slide images because each whole slide image is one sample. And that's not always possible. For instance, in the cohort we are studying for HCPs in clear cell renal cell carcinoma, we have only about 250 cases, which does not form an adequate sample size to do this weak supervision. So the alternative is to do tile level supervision. So we can, for instance, annotate histologic growth patterns by drawing polygons on these whole slide images, and then we can sample tiles inside these polygons. In fact, this is what we did in collaboration with our pathologists. So they annotated 53 whole slide images in this way for us, and this gives rise to approximately 5,600 non-overlapping tiles. And of course, many more tiles are available outside these polygons or from completely annotated whole slide images. So we want to approach this problem as a semi-supervised learning problem. We want to leverage unlabeled tiles. And in doing this, we want to use tools from contrastive learning. So that brings me to the second part of my talk. So I want to introduce briefly consistency regularization and contrastive learning, and then talk about our method of stain-based contrastive learning for H&E images. So we introduced this concept of consistency regularization in a 2016 paper, and our idea was that geometric and color transformations of a training sample do not change its label. Therefore, we can formulate an unsupervised loss which penalizes the differences in predictions of the model when fed different transformed versions of the same sample. And because we don't need to know the label to formulate this loss, it's an unsupervised loss, which can be then used with a limited amount of label data in a semi-supervised learning framework. A concurrent work, temporal ensembling, takes a very similar approach. And of course, there has been many improvements to the consistency regularization framework over the years, such as improved formulations algorithmically like mean teacher, improved data transformations, virtual adversarial training, mixed match, fixed match, and flex match. Next, I want to briefly talk about contrastive learning. And one of the earlier losses used for contrastive learning is the triplet loss, which relies on this concept of a triplet where you have an anchor sample and you obtain a positive sample via transformation of the anchor, such as geometric and color transformations as used in consistency regularization. And then you can pick a negative sample randomly. And the idea of the learning here is to bring the positive sample closer to the anchor with respect to the negative sample in the feature space as you're learning. The advantage of this approach over the consistency regularization is consistency regularization by itself will collapse to a point as constant in the feature space if you don't have label data to balance it. So it cannot be used by itself. On the other hand, contrastive learning, such as the triplet loss, can be used in a self-supervised manner because of this effect of the negative point. It will not collapse to a trivial solution. Later, works on contrastive learning, for instance, introduced the instance loss, which defines learning as discrimination across instances instead of classes. And because of the large number of instances, of course, it uses noise contrastive estimation. Perhaps the most popular, well-known example of this type of work is Sinclair, which composes complex transformations by cropping, scaling, color distortions, and blurrings on images, and then learns by discrimination across transformed instances and uses a projection head. So with the advent of these methods, the accuracy gap between supervised and self-supervised learning has been closing. And as we know, contrastive learning forms one of the hottest topics in machine learning research. So the next thing I want to talk about is multimodal contrastive learning. And a great example of this is contrastive language image pre-training. And in the context of medical images, for instance, the CONVERT model takes chest x-rays and associated radiological reports and learns in a contrastive manner. So here we have two encoders, one for the image and one for the text. And the idea is to bring in the feature space the features obtained by these encoders closer together if they are coming from a matched image report pair, and to push them apart if they are coming from different patients. So this brings me to our idea here. And we're working with hematoxylin and eosin images, H&E for short. These are the standard for clinical pathology. And our idea is to use hematoxylin and eosin stains for multimodal contrastive learning. We think that this is a good idea because the H stain will stain nuclear regions and has a purple color. The E stain will stain cytoplasm and extracellular regions and has a pink color. They're typically captured together, of course, as a RGB image, and the H and the E channels are not readily available. Now, one of the reasons we think that H and the E images can form a good multimodal basis for contrastive learning actually goes back to co-training. So co-training is one of the early approaches, one of the earliest approaches to semi-supervised learning by Mitchell and Bloom from the 1998. And just to briefly describe this, in co-training, you have two classifiers that are trained on different views of the data. View here means features. And they produce pseudo labels for each other on the unlabeled data. So in a way, they teach each other. The assumptions that go into co-training is that each view on its own is sufficient to support accurate classification, and also that the two views are conditionally independent of each other given the class of a sample. So we believe that the H&E stains largely fulfill these assumptions because, as mentioned before, the H stain will show us the nuclear regions in the image, whereas the E stain will show us cytoplasm and extracellular regions. And there has been previous work to try to recover the H stain and the E stain from captured RGB H&E images. So for instance, a 2001 paper provides a linear transformation in the logarithmic RGB space to recover approximate H and E stain channels. And this is the work we adopt to do the same to get the H and the E stains for an image. So then our learning framework that we propose goes like this. After we separate an RGB image into its H and E channels, then we will pass both through a ResNet 18 model in this case. We'll call these the H ResNet and the E ResNet. Even though they share the architecture, they're separate networks. They have separate weights. The features produced by these networks FH and FE will, because we want to produce a shared feature space between these two channels, we will average them element-wise, and then we'll have a final fully connected layer for whatever classification task we're interested in. And for learning, we'll have, of course, cross entropy on that classification for our labeled tiles, but then we also will define a contrastive loss in the feature space on FH and FE, which can work with all tiles, labeled or unlabeled. And the final loss for learning is, of course, a weighted combination of these two things. So next, I want to tell you a little bit more about the contrastive loss here. So take a tile, let's call it XI. This will be our anchor tile. And we separate this into the H and the E channels, as discussed before. And what we want is, because this is a shared feature space, we want these two features to be very close in the feature space, right? FH and FE from XI should be very close because even though they are different views, they share the same latent variables of what is going on in that tile. Now, to prevent feature collapse, as in contrastive learning, we need a negative point, and this can be a tile XK, which is randomly chosen. Because it has different information, its H and E channels form negative pairs with the H and E channels of our anchor, right? So the idea then is to use a triplet loss, which pulls together the H and E features from the anchor tile together while pushing the negative one away from the anchor, right? We want the FH and FE from our anchor to be closer together than when we compare them to the FH and FE from the negative pairs. So it's a relatively simple idea. So we want to next talk about some experimental results that we got with this method. So to give a little bit more detail about the data set that we're working with. So as mentioned, we're working on histologic growth patterns for kidney cancer, specifically clear cell renal cell carcinoma. And we're looking at two classification problems for now. One is diffuse versus non-diffuse HGP morphology, and the other is favorable versus non-favorable HGP morphology. And as mentioned before, our group annotated 53 whole slide images by drawing polygons, and we got a number of tiles from these data, from these polygons. We set aside 4,100 or so for training, 630 or so for validation, and 840 for testing. We'll make sure that the tiles in the validation and test set come from separate patients. So we separate at the case level, the testing and the validation sets from the training to make sure that we have a realistic and challenging scenario. Some learning details. So we're using a ResNet 18 as a backbone. Because of the limited amount of data we're working with, we thought ResNet 18 would be a good choice. We're doing your typical augmentations with color jittering, rotations and croppings and flipping. Okay, so, and we want to start by comparing the proposed architecture, this H&E contrastive learning architecture, as we want to call it, to a baseline model, which is a standard ResNet, which operates, of course, on a color image, the RGB image. And we see here that, when we look at the training accuracy across both tasks, both of these models perform nearly perfectly, which means that ResNet 18 is sufficient to solve these tasks. Now, if we look at the testing accuracy, though, the baseline model actually suffers from moderate to severe overfitting depending on the task, especially on the diffuse versus non-diffuse or nested task. It has about a 15% accuracy gap from training, which shows pretty severe overfitting. Now, if we look at the proposed contrastive learning model, we see that it suffers much less from overfitting, even though having almost double the number of parameters. Remember that the proposed model has actually two ResNet 18s with single channel inputs to encode both the H and the E channels. So we believe that the contrastive learning has a strong regularization effector, which is resulting in less overfitting. So next, we wanted to look at semi-supervised learning. So what happens if we have even less labels than we have now? To do this, we downsample our training set by a factor of 10 to get labeled samples, so 10% label samples. And not surprisingly, when we perform the baseline model with such a limited training set, we get much lower accuracies. These are all testing accuracies that are being shown at the slide, and these are testing accuracies at the best validation epochs. So 70% instead of 80 and 90% is what we get. Now, we can also look at some state-of-the-art consistency regularization based methods such as mix match and fixed match and how they do on this data set. Of course, these are general purpose semi-supervised learning tools from computer vision, which I briefly introduced earlier. And they do well. They improve the accuracy quite a bit. But of course, one thing they don't do is they don't use the specific nature of H&E images. And this is where we think our model maybe has a advantage. So the contrastive learning model of H&E stains with 10% label data actually does quite well. In fact, we don't see much of a difference at all whether we use 10% labels or 100% of our label set for learning. We get very similar results in terms of testing accuracy with the proposed model. So that's good, but then we wanted to kind of ask some more questions to understand better what's going on. First, we wanted to ask, is the contrastive loss important, or are these accuracy gains only due to the H&E inputs rather than the RGB inputs? So to do this, we can keep the same architecture, but omit the contrastive loss. And if we do that, we see that there's really no difference in accuracy, testing accuracy from the baseline model, which is a single RGB ResNet. And these are, of course, much lower than the actual proposed model, which combines HE inputs with contrastive learning. So from this, we concluded that yes, contrastive loss is important. Then we want to ask the flip question, which is the choice of HE inputs important, or are the gains simply due to the contrastive loss? What happens if we use pairs, for instance, from the RGB channels with the contrastive loss. Of course, the really proper way to do this would be to have like free channels with the RGB separately, but for now, we're just taking pairs from RGB channels, for instance, the red channel and the green channel, and we're passing them just like we do in the proposed model into separate ResNets and coding them and using the contrastive loss and the color entropy for learning. And when we do this, we see that actually contrastive loss or no contrastive loss gives the same result. So contrastive loss is not able to leverage the RGB inputs like it's able to leverage the H&E inputs, which also brings us to the conclusion that from these two studies, from these two ablation studies, we can conclude that it's the combination of the H&E inputs and the contrastive loss that is crucial for this improved accuracy in learning. So finally, to explain this a little bit more, I want to go into a little bit detail about this co-training assumptions and how maybe the H&E inputs fulfill these assumptions, because we think that it's really this point here that makes a difference. So first is the simpler one, which is co-training assumes that each view by itself is able to support accurate classification on its own. And so we tried this. We tried just a ResNet which works only on the H image and a ResNet which works only on the E image, and looked at its testing accuracy for the different tasks. And while we saw that for most of the cases it's slightly lower than the baseline model, which actually is not too bad. So these views on their own, at least for the tasks we've chosen, are able to support somewhat accurate classification. The harder part, perhaps, is to assess whether they are conditionally independent. And we cannot really do that directly. However, what we could do is we can look at how these views are correlated to each other. So what we did is we trained UNet models to predict different channels from each other. What that means is we trained, for instance, one UNet model to predict the E image of our H&E image, the E channel from the H channel of our H&E image, or the H channel from the E channel of our H&E image. We also trained to predict, for instance, the green channel from the red channel and vice versa, and for different pairs of the RGB channels. And then at testing, we look at the coefficient of determination, the R-square value, for these different mappings to see how well we can predict the other channel. Of course, the R-square value of 1 means we can perfectly predict, and 0 would means we cannot predict at all. And what we see here are the R-square values for the pairs of red, green, blue channels are actually much higher compared to the R-square values for the E and the H channels, which means for us that it's much harder to predict E from H compared to, say, predicting G from R, which is perhaps not surprising based on, again, the fact that H and the E view channels show different things, the nuclear regions and the cytoplasm, and the RGB channels are much more correlated. But this kind of numerically puts that on firmer ground, and we think that this is one of the reasons that this framework works well. So with that, I want to talk about some conclusions and future directions. So we've shown contrastive learning with H&E views improves accuracy of classification independent on the number of label tiles we have. It can be used in a supervised or self-supervised learning framework. In fact, it could also be used in a self-supervised learning framework as a pre-training step. We haven't done this yet, but because contrastive loss, unlike semi-supervised learning, will not collapse, it can be used for pre-training. We can also use unlabeled tiles outside the annotated polygons to significantly increase the training size for our contrastive loss. Again, this is not something that we have done yet, but we plan to do this, and we think that it will allow us to tackle finer-grained classification tasks. And we want to apply this method to other data sets and pathologies. And finally, we want to see if better approximations of the H and the E channels in place of the simple projection that we use currently, would that create more conditionally independent views and perhaps improve the results further. Finally, I want to acknowledge my student Bodong Zhang, which did this work, and of course our pathology collaborators Beatrice Knudsen and Deepika Sirohi, who painstakingly annotated these images and also gave us very valuable feedback from the pathology point of view, and our funding support the Computational Oncology and Research Initiative at the University of Utah. If you're interested, the paper and the code for this can be found on the links on this slide. With that, I want to end and thank you for your time, and I'm happy to take questions if there are any.
Thank you, sir. Thank you, Professor Tolga Tasdizen. Thank you for excellent speech. Is somebody have any questions? Please feel free to ask. If you have
Maybe
any
I can. Yeah, maybe I can ask. Again, another very excellent presentation. Thank you for that. My question is that I am a biochemist. I have no idea about computer science, but I have collaborators who seems to be helping me with that. But what my question is that if you have to use pathology slides or these images from somewhere else, would your program still work? Because what I'm seeing that you have data from different sources or different cohort, and every time it just doesn't give you the results you expect. So how do you overcome with these issues? Do you then start all over again, combining everything and doing training and testing, or certain programs?
That's an excellent question. In fact, I have another slide here, which does kind of what you said. So we apply the same approach to prostate cancer, but in this case, we actually trained on data from our institution, from the University of Utah, and then used the TCGA cohorts for validation and testing. And what you can see here is like the same conclusions that I presented to hold, but the absolute numbers are much lower. Instead of being up in the 90s, they're like in the high 70s, the accuracies. And of course, probably the primary reason for this is because the data is coming from two different institutions, the training data and the testing data. So this is known as domain shift in computer science and machine learning. And it's a big problem if you're testing data, when you apply your model to a different cohort, which has different characteristics, be it the way it was stained, it was imaged, or something else, accuracies suffer. There are ways to partially address this, and we haven't done this for any of this results on this slide, but there are domain adaptation methods you can use to adapt your model in an unsupervised way to the other institutions' data, and it would improve accuracies probably significantly. And you can do other things. There's active research going on in this area of domain invariant learning, adapting models at inference time. But it is really the answer to your question. It's an open area of research. There are significant improvements when you use these methods, but still, I don't believe that it comes to the same level of accuracy if you had training data from the same institution and applied it there. So it's still work in progress. It's an open and very important question. Yeah.
Right. Can I just follow up with another one? So I look at the protein damage markers and the biomarkers in blood, and we use gold standard technique, which I have applied all over the world, and we have similar results, but of course there are some variations. So what I would like to know is that if you have from one institute, the changes of certain biomarkers are significantly different, but then another institute or another country, those changes are not highly significant different, but still the trend is the same. So why machine learning doesn't kind of pick those patterns then? Or is there a way to pick up those patterns which are still the similar direction, but are not as highly separated cohort or biomarkers from cases to control?
So I am trying to understand your question. I think you're asking what happens or why if you have a different cohort, which perhaps has a slightly different set of biomarkers that are important than the initial cohort, then why machine learning cannot deal with this very well? Is that
no,
the question?
it's this. No, same biomarkers. Is the changes are slightly different. Let's say there are 4 biomarkers and 3 in one institute were highly significantly different from control. the cases were, but in the second institute or country, the changes are different, I mean, but not highly significant.
Okay, well, I think this is actually very related to the first question in my mind. I mean, I think this differences between the two institutions or two countries or two domains, if you will, is what leads to the problem. So machine learning or current machine learning methods are all data driven. They only learn from the examples we give them, and they are not really learning something holistic beyond that. And so they're not learning like a human would. And they have a hard time adapting anytime the specifics or the numerics of your data changes, unless you tackle that problem with some method like domain adaptation. They will suffer because they're fine-tuned to the specific differences they see on the training set. And that's what they look for in the other cohort. So that's the shortcoming of current methods for sure, current machine learning methods for sure, because they're simply data driven, and most methods anyway. I shouldn't exclude there's definitely research in physics-based machine learning and other approaches which try to incorporate domain knowledge into this, but they're the exception at the moment rather than the norm. So if we do traditional machine learning, we suffer from this data-driven view only. Yeah.
I see. All right. Thank you so much for explaining.
You're welcome.
Thank you. Thank you for your excellent conversation.
Thank
Any
you.
other questions? If there are no questions, let's move on to the next keynote speech. Thank you, Professor. Thank you.
Thank you once again.